Test. Okay, the mic's working. And well, first of all, thank you all for coming here. I'm surprised how many of you are missing out at Jones Skid Store on the C#7. So thank you very much appreciated. I guess before we start, I just want to quickly ask the room, how many of you guys are actually working with some form of function as a service, Azure Functions or AWS? Okay, quite a few hands. Great. And how many of you are working with AWS in that case? Okay, quite a few hands. Okay, a few more people coming in. So for those of you who are working with AWS, good news is that they actually just announced yesterday support for .NET Core 2.0. I see some fist bumps at the front. And also support for Golang as well. So if anyone wants to try out AWS Lambda with Golang and .NET Core 2.0, now is a good chance to do that. Just going to wait for the guys to settle down. All right, so my name is Yan, and I've been using Amazon Web Services since about 2009. And in that time, I've worked for quite a few different companies and took on a few different type of roles. Right now, I'm working for a company called Space 8 Games. I can see from my T-shirt. We make mobile games for a living. And unfortunately, I can't talk about anything I'm working on because it's so heavily NDA'd. If I tell you, I'm going to kill you afterwards. But what we can talk about is some of the things that I did at my previous company, which is a social networking startup called Yabble. We actually worked with my friend and former colleague, Domas here.
So my name is Domas, and I started using AWS in 2012 when I joined GameSys to work with this guy. And then he poached me to come over to the startup Yabble, the company that we're going to be presenting our experience report. Do you want to take one?
Yeah, sure. So I can see our bromance goes a long way. Right, tell you a bit about Yabble. So at the time, we were trying to build a new social network for your 20-something years old, and it was a mixture of Instagram, Twitter, and Facebook. And it was when we were working at Yabble that we learned a lot about working with AWS Lambda and how to operate it in production. It actually became a very prominent part of our architecture, which when I took over at Yabble in April 2016, we had a very simple, on paper at least, architecture at the time. It was all monolithic. There's a few services running on EC2 servers. And as the early sort of social network, we had a pretty low average traffic. There's not many people using it, but we did have a couple of power users with, I think the most popular user we had about 50,000 followers. So whenever one of those guys does something on a campaign, like I'm going to give away some designer handbags for anyone who votes on my post by 10 o'clock tonight. So whenever they do something like that, we see a massive uptake on traffic. Sometimes from 1 minute to the next, you have a 70 to 100 times jump in traffic. And everything is running on EC2, so scaling was pretty slow. And so we have to run at a much lower utilization than we like to leave some room for some of those massive spikes we get. And also we have to scale up a lot earlier, again, because of all these sudden spikes in traffic. At the time, we also didn't do very good. We didn't have a very good infrastructure in place for doing deployments, and deployment was taking up to 30 minutes and required downtime. So you put all these things together, it means that we are both paying a lot of money for resources that we are not using, and B, we are we are losing availability whenever we need to do an update. So that's not great, especially by today's standard. And one of my favorite speakers, Dan North, once said that the lead time to someone saying thank you is the only reputational metric that matters to us as engineers. But to get that thank you, you have to first deliver some value to someone. And to do that, we have to ship our software. Until our code is shipped and running in production, as far as the users are concerned, we haven't done anything at all. So we join a team, we see that the architecture in place is not great, we have to do better. But before we can hope to do that, we have to first understand and figure out and agree on what good actually looks like for us in this case. And we sat down with the team and we came up with a list of criteria that we think that we're going to need from our architecture. Firstly, we want deployments to be small, to be fast. And we obviously do not want to have any downtime at all. And also, we don't want to be in a situation where we have to do lockstep deployments with the client team, which just the sheer amount of coordination and stress involved is just not worth the while. And we also want features to be independently deployable and to be loosely coupled through messages. so that different components of the system can move at their own pace. And from the architecture side of things, we want to cut out all the fat we had in our AWS build, and we also want to minimize the amount of time that we spend just babysitting the infrastructure. As far as I'm concerned, the architecture should work for us, not the other way around. It shouldn't be a constant tax on the team to make sure that it's working and making sure that, oh yeah, it's scaling up right on time and fast enough. All of that should be taken care of by the platform itself. And at the time, we also had lots of technical mess to deal with, and that's a very conscious choice of wording, because if you talk about technical debt, it implies that someone has at some point had made a design decision to take out some debts with a plan to pay it back later. What we found at Yabbo was not that. In fact, it was quite messy. If I was to go, I could spend a whole hour talking about how bad it was, but that's not what you're here to hear. And whilst we fix all this technical mess, we also don't want to just take 6 months out and clean out the code base. We want to keep shipping features, keep delivering values to our customers. In fact, we want to do it faster than we've ever done. And if you fast forward just a few months, this is the architecture that we arrived at, which is both event-driven as well as the service-oriented, where Lambda is a centerpiece that glues everything together. So at this point, we had about 170 Lambda running in production, with many more that were still in development. And we were paying for Lambda invocations about 5% for what we pay for EC2 for a comparable amount of compute resources that we're using. But perhaps more importantly, from the cost saving, is how quickly we're now able to ship features and ship code to our users. And going from doing production release maybe 4 to 6 times a month, in April, by October, we were easily shipping code to production somewhere close to about 100 times a month. So that's a big increase in terms of the output of the team, without actually changing the massive increase in the size of the team. And from the moment we decided Lambda is a good fit for the direction that we want to move towards, and to having that first function running in production, we had to, as professionals, and we have to be responsible. We can't just say, hey, this tech looks good, let's just put it into production without actually knowing how we're going to operate it. So to do that, we had answered a bunch of questions around how you're going to test your functions when they're all hosted in the cloud, and what about your CI/CD pipeline, and how do you do logging, monitoring, and alerting, and so on. The thing to remember is that as great a tech as Lambda is, or any form of serverless technologies, they are just still tools. And typically, when you change the tools that you build software with, often the practices and patterns that have emerged with the previous generation of tools, they will have to change or at least evolve and be adapted. But the principles that underlines the emergence of those practices, they still very much apply. You still need observability, another hot keyword in 2018, on your architecture to understand what the hell is going on, to be able to operate it responsibly in production. And there's also a bunch of other principles that you still follow, principles around high cohesion and low coupling and single responsibility and so on and so forth. And by the time our architecture expanded to include more and more services, often one service will depend on another one, you have to answer a bunch of other questions around distributed tracing, how you're going to manage configurations for hundreds and thousands of functions running independently in production, and how you're going to keep all of the information that you have secure as well. And for now, I'm going to awkwardly pass it to my colleague, Domas.
So to start off, I think it's good to give some concrete examples, what we actually built, what we achieved. And the first thing we tackled was search. Because when you have a social app, you want to find somebody to follow. So to get that, you want to search by first name, by last name, by username. And what we actually found in the legacy monolith, it was search implemented using regex that was hitting MongoDB. And you can imagine that performance was not really great. It was actually struggling at the 100,000 user mark. What currently, like in this day, for a social app, it's nothing. You want to have at least to be handling millions of users easily. And at that point, for us, it was difficult to do any kind of rudimentary ranking system by popularity, or maybe trending users should be on top. So we started off to build something from scratch, simple search. So what we did, we looked at the monolith without many modifications. We just allowed it to emit state change events. So that means whenever new user is created, or somebody changes a name or updates their profile, we want to raise an event. Then we had all of those events being published to Kinesis Stream, and we had a Lambda that would process them and update index in Amazon Cloud Search. Then we could take API Gateway and Lambda, put it on top, and easily make a new search API that would query Cloud Search. But at that point, we did not want to impact existing applications, and we did not want to wait until our client devs are ready to start using the new search and actually even release the app, and then users need to update it. So instead of that, what we did, we just proxied legacy endpoint to actually start hitting our new search API. So in this way, we delivered value early on without waiting for app release. Also, we had no analytics at that point. So to do that, we also had to build everything from scratch, and we did that over many iterations. But for the first iterations, we followed similar pattern where we updated our legacy system to start emitting detailed events about all the actions that our users are doing in the app. All of those events are going through Kinesis streams and being handled by Lambda. And then Lambda is live streaming all of those events to Google BigQuery. BigQuery is amazing for large amounts of data, and this is something we used previously in the GameSys where we worked before with Yan, so we knew that we can, it's a really good fit. And actually, to get this first iteration out, one developer, it was his first he had to deal with Lambdas. This was his first piece he had to implement using Lambda. And actually, from design to production, it took only 2 days to get that. And our BI guy came to us when we said that it's done, and he tried it out. And he was amazed. He said nothing ever got this done this fast in Skype, and where he just came from. And of course, no offense to Skype, but it just shows that lead time to someone saying thank you, that's the only metric you really need to care about. So we got a bit more comfortable with using Lambdas, shipping them to production and so on. So the next thing we tackled was a feed. As you can imagine, like in an app, you open and you see all the posts from people you follow, so similar like what you have in Facebook or in Twitter. So the legacy implementation was really complicated. It was just a mess to untangle. And actually, when they were implementing legacy, they've written a huge spec. So there was a document listing every single use case that it should support. And then when QA team picked it up and tried testing it, every single one of them failed. So they just declared it untestable and actually refused to test feeds at all. And to top it off, at that point, new CTO came in. So this all happens in the legacy still world. So when new CTO came in, he looked at the mess that's current system is. He actually fired the whole team that was involved in creating such a mess. And so when we came in, we had nobody to actually ask how it should behave, or more importantly, why the hell they built it that way. So we had to build it from scratch. We sat down with the product team to figure out what our actual requirements are, and we did in a similar fashion where everything is based off of events. So legacy system is publishing events such as I'm following somebody, or somebody I'm following posts creates a new post. So I wanted that post to appear in my feed. So all of those events were being handled by Lambdas, where Lambda sees that, okay, new post just was published, and needs to get the list of everybody to everybody's feed where it needs to go. So this operation is quite costly. So what we did, we got all of them, the feeds where it needs to go, all the destinations. We batched them up by 100 or 1,000, it doesn't really matter, and then published via SNS. So then we had another Lambda listening to that SNS feed to update sorted sets in Redis. And at this point, we're getting retries between SNS and Lambda. So we are retrying at this point, but so we don't have to retry from the start the costly operation of actually getting the list of the followers, because somebody might have thousands of followers, and that operation, retrieving that list, might be quite costly. Right, so we using Redis to have a sort of set, and then we just building an API in front of it, where we just have API gateway and Lambda, the same pattern as you've seen before, and then we updating legacy system to proxy the old endpoint to actually hit the new APIs. So at that point, we also wanted to tackle a bit more complex situations, which is recommendation system. So it's what we found in the legacy system was anything unlike Facebook or Twitter. It was actually returning you the first 30 people from the database by account creation date. So that means it was all Yebble employees that started off and created their accounts first. So it might be great for them that everybody's following them, but actually if, as a customer, like if you open an app and you want to find somebody to follow, it's useless. So we started off simple. We already had old analytics in BigQuery. Then we had just a simple cron job that kicks off every hour or so. And so it's a CloudWatch event, a schedule event that just works as a cron job, which triggers a Lambda. Lambda hits Google BigQuery. BigQuery is good for this case because it can process huge amounts of data in a couple seconds or tens of seconds. So then we, by using a simple time decay function, we can figure out who's trending at this point, and then update the trending users list in DynamoDB. Then we built API on top of it by using API Gateway and Lambda to just query to get the list from of the trending users from DynamoDB. At that point, we built the other way, because it's good to know who's trending, but also you want to know who your friends are following, because if I'm following somebody, I'm probably going to be interested to follow the same people that that person is following. So we listen to the events being published by legacy system for any relationship changes. So if you unfollow somebody or follow somebody new, we had a Lambda to process those events and update GrapheneDB, updates your social graph who you're following. GrapheneDB is just a hosted version of Neo4j. Then we build an API on top with API Gateway and Lambda. And to top it off, we proxied that legacy system to hit both these new APIs for the recommendations from your relationship graph, and also to get the trending users. And now the old apps can still work as they were with no changes. And to achieve this, the first bit, the BigQuery, I think Yan took like 1 night or so to implement the lower part of this, and maybe another couple days to do the whole social graph thing. So it just showed how quickly we could get a feature from design to production really quickly. And these are just a couple examples what we actually achieved. There is plenty more. There is a lot of posts on Yan's blog that you can, to the fun part, what to do when you're actually getting to production.
Thank you, Domas. So I guess the number one thing I would say about in terms of getting ready for production is don't try to reinvent a deployment framework yourself. I've done that in the past when none of the frameworks are quite ready yet. And one of the things you really quickly learn is that there's so many nuts and bolts you need to understand of the underlying infrastructure, and to get it right is really hard. And all the frameworks that you see available on the market today, they've all gone through that learning process, making mistakes, fixing it, and the one that we use is called the Serverless framework, and one of the reasons why we chose it is that it's backed by a financial company. Even at the time when we adopted it in 2016, there was a lot of momentum in the community. But also at this point in time, they've gone through that first version where they made a lot of mistakes, and they've heard the feedback from the community. And now there's version 1, and version 2 is not far from in the horizon. But since then, Amazon also got himself into the game with SAM framework as well. And between Serverless and SAM, these are the two biggest deployment frameworks at least for AWS Lambda. One thing to keep in mind is that serverless framework supports other providers as well. So it supports out of the box via plugin. Well, out of the box Azure functions, Google Cloud functions, Spot-Inst, OpenWhisk, and more are available and also added constantly by the community via its very extensive and also very flexible framework plugin structure. But then also there's Apex, there's UP. Cloudia, Zappa, Sparta, so symptomatic of any new and hyped technologies. Just a new framework just about every single week. And I think I saw another one last week called Archicode or something. I think the point I'm here to make is that there's going to be a lot of new frameworks, and rather than getting yourself distracted with all these new frameworks and trying them out, try a few of them, pick one that works best for you and your team, and just mandate that on the team. You don't want to waste so much time just jumping between different frameworks, and also you want to maximize the amount of knowledge sharing within your team. At the same time, minimize the friction that you're going to cause when people move from one project to another. When I go to a different project that maybe Domas is working on, I want to focus and spend my time learning the new domain, the new code base, rather than working out, okay, so I was using serverless to do my deployment in the previous in the previous project, now they're using something else, how do I deploy my code? Those things should become institutional knowledge in your team. You don't want to be wasting people's time learning how to deploy your code every time they move to a new project. But once you start working with Lambda, you're going to have to figure out how do you test your code. And as far as testing goes, this is my favorite book by Ned Price and Steve Freeman. And it talks about the different levels of testing. First, you've got your unit test, where you test your code at the object or module level. And nothing's changed here. Ultimately, if you've got some business logic encapsulated into a class or a module, you can still write code that tests them the same way as you have always done. And then you've got the integration test, where you test your code against code that you can't change. And since Lambda ultimately is just some function, some business logic that Amazon is calling on your behalf when some event happens, there's nothing that stops you from exercising the same code by calling your function locally with a stubbed event and context object. That way, you can still exercise the same logic locally as you would do when it's executing in the cloud. The thing to keep in mind is that the purpose of integration tests is to exercise your code against code you can't change. So when you're running your integration tests, it's important to set them up, even when you're running them locally, to hit the real downstream systems that you're talking to. It's my strong belief that you shouldn't be using mocks and stubs for this kind of tests. Otherwise, you're going to be learning my code works fine against my stubs. And the moment I deploy it to production, bam, because the thing that I'm stubbing doesn't behave exactly the way that my stubs do. And once your code has been deployed to and run it inside an AWS environment, you can then run acceptance tests, where you test whether or not the whole system works end to end. And as you go up this triangle of testing, the unit tests give you a much faster feedback loop, but you get a far stronger sense of confidence with your acceptance test that what you've got here is actually going to do what you're supposed to when it's deployed into production. And one of the key things I learned from this book, and I'm going to read it because it's quite long, is that we find that tests that mock external libraries often need to be complex to get a code into the right state for the functionality that we need to exercise. The mess in this test is telling us that the design is not right, but instead of fixing the problem by improving the code, we have to carry the extra complexity in both the code and the test. And the second risk is that we have to be sure the behavior that we stub or mock matches what the external library will actually do. And even if we get it right once, we have to make sure that the tests remain valid as we upgrade the libraries. Now, the same principles, I think, still apply in this increasingly service-oriented world that we live in, that you really shouldn't be mocking services that you don't control. Think about how the second risk that Nat and Steve talked about, that you have to make sure that your mocks continue to work when you upgrade the library. Now, when Amazon updates one of their services, you are not in control of when they do that, but you still got to make sure that your stubs and your mock still matches exactly what the new version of a service is going to do. But I think fundamentally, we have to rethink how we test software when it comes to serverless technologies like Lambda, because I think that the risk profile of what can go wrong has fundamentally changed. If you focus on testing what's inside your function with your unit test and just mocking and stubbing your dependencies, you're missing out most of the things that can actually go wrong when your code runs in production. For me personally, the first thing that often goes wrong is IAM permissions. I created a new function, it's using a new table, and it all works fine when I'm using mocks and stubs. The moment I run it and deploy it and run it, bam. Okay, my function can't talk to the DynamoDB table because it's missing the permissions, or there's a whole bunch of orchestration involved in terms of the creation, the maintenance of those resources my function is using, the configuration of upstream event sources, and so on and so forth. And this risk of shipping broken software due to misconfiguration is vastly magnified when you have to do manage the configuration for every single one of those hundreds and thousands of functions that you're going to have running in production. And it's my observation that most of your Lambda functions themselves are actually now very, very simple. If you apply the learnings we have done with single responsibility, the individual functions themselves are normally very, very simple. The risk of you actually shipping some broken code has now largely shifted to how your function interacts with external services and its downstream dependencies. And since the whole purpose of us of writing tests, the whole purpose of us of writing code in the first place is so that we can ship working software at the end of the whole cycle. And that's the goal that we should ultimately optimize towards in terms of how we work. So as far as I'm concerned, it's okay for me to lose some of my feedback loop speed, even though I love it as a developer. But ultimately, if I'm learning the wrong things faster with a fast feedback loop, that's not going to help me ship working software faster to my users. And recently, in the last, 6 months, we also start to see some of these local, environments. With AWS, you've got AWS SAM local. There's also some tool from JetBrains as well. I think those tools are great, and they're definitely very helpful in certain stages of your development cycle. But you shouldn't use them in place or instead of your end-to-end test. You should still be writing end-to-end tests and making sure that your code is running, is going to work the way you expect it to end-to-end. And that means you have to rely on a lot of external services during your testing. And I think that's okay. As Paul points out, there's so many services for you to choose. If one doesn't work quite well for you, just pick another one. There are just hundreds of them out there nowadays. As for end-to-end testing, Steve and Nat also talks about how, wherever possible, an acceptance test should exercise the system end-to-end without calling directly its internal code. An end-to-end test interacts with the system only from the outside through its interfaces. And going back to the search API example that Domas gave earlier, to test the system, we will interact with the legacy system via its HTTP interface the same way that our mobile client would do to create new users. And the test case would be to validate that within a reasonable amount of time, those new users then can be searched by first name, last name, and username by talking to the search API directly. Another thing we notice is that when you're running your integration test, you're testing your code locally, but hitting the same real downstream databases and message queues and so on. But when you're testing your system with acceptance test, you're talking to the same code, but instead you're talking to them via HTTP endpoints or SNS messages and so on. So the only difference between these two is how your code is being invoked, right? So when we're writing the test, we can actually reuse the test cases by defining the when step. So when we invoke some endpoint, a get endpoint, so inside the definition of that when step, we can have a toggle which can be passed in as environment variables or any other means that you can that you want to use instead. And where in this case, if it says it's handler, then we'll call the handler function directly with a stub event and context. But if it says something else, then we'll call the HTTP endpoint that's been configured as part of our test setup as well. And you can see how this works. You can try it out yourself as well. I've got a GitHub repo where you can actually see how this can be configured for your own use case.
And this is where we get to CI and CD. Because this is something, there was always temptation to leave it at the very end, to automate your deployments, automate your tests and so on, because it takes time. But actually, the earlier you consider CI and CD, the more time you're going to save in the long term, especially because that's going to avoid all the human errors that you could have otherwise. And especially because there are tools like Serverless, you have no excuse not to use it, because Serverless makes it so simple to deploy. Just single command that you run on command line, done. Other things you need to think about, how you're testing. So coming back to the same book that we really like is how Steve says that we prefer to have end-to-end tests exercising both system and the processes by which it's being built and deployed. This sounds like a lot of effort, because of course it is, but has to be done anyway, because during the development of your system. So no excuse not to do it. And another pet peeve of Yan is that he's always annoyed when configuration in your TeamCity or Jenkins or so on is not versioned. So when something breaks, you're not going to know who changed it, you don't know why it changed it, and more importantly, you don't know what it was before, so you can't revert it back. It just wastes time. And moreover, it should be repeatable both on the CI box and your local machine. So what we had in YAML, we were using Jenkins. So the main principle was we wanted to have, it might be difficult to read, but the command to run unit test and integration test was just one single command with bash script with a couple parameters. The same way to do a deployment, the same build bash script with a deploy parameter to run acceptance test and so on. So now the whole configuration can be run both on your local machine when you're looking why your deployments are failing. You don't need to have a really slow cycle where you change something and then you need to wait for Jenkins box to actually kick off the job and build it. You can just do that all locally. So what we had, as you can see, like quite a small bash script, but importantly, especially if you're using serverless, a thing to keep in mind is, if you look there where the Node modules is listed, we're using local Node modules, because in Node.js you can install packages either globally or locally as part of your project. So I would suggest do that locally. So now the build process is independent of what it's installed on your build machine, because now if serverless does a breaking change, you're not going to break all your builds, because the builds are going to be using the version that they depend on and that you configured. Also, I would actually recommend to instead use Jenkins file that could be versioned and controlled together with your project. But if you do that, still follow the same principle. The build command should be just single line that you can easily run. It should not have some special logic about how you run it and what you do. You still want to be able to do just really simple small command. Another thing we had to consider is whether to do continuous delivery or continuous deployments. The only difference between those two is basically how your code gets to production, whether it's automated or it's manual. In YAML we had that as soon as you push to master, we're going to build it, we're going to run all the integration tests, unit tests, deploy it, run acceptance test in the dev environment, in test environment, and staging, but it's not going to go to production just yet, because we wanted to have that control about when it goes live and what goes live, just to be sure. And especially we had a rule to never deploy on Fridays evening, because I'm guessing in many London offices you might have a beer fridge and so on, and you don't want to be, after a couple of beers, deploying to prod and then just going home all happy. So next we're getting to logging, because it's all good and fine. We deployed our systems to production, but now when the bug comes along, how do you diagnose where it got? So with Lambda, it's quite simple. Anything that you print out to the standard output are going to be shipped to the CloudWatch logs, and additional information is being appended as well, like the timestamp when it happened and the ID. For example, if you're using API gateway, it's going to be the request ID. So having all this, if you're not familiar with how the CloudWatch looks in the AWS console, you have the cloud log group that actually the name matches what your Lambda name is. So there is one log group per Lambda, and then each specific version and execution of the Lambda will create a new log stream. So, but the problem is that CloudWatch is not really easily searchable or using, especially when you have hundreds of Lambdas running and you easily gonna get overloaded with all the logs. And this is a really common problem with microservices. So the solution for that is centralized logging. So for the centralized logging is going to make them easily searchable. So one of the industry standards is elk stack. This is what we chose to use. It could be anything. It could be Splunk or so on. All of these principles are going to apply to any of those systems. So the good thing about CloudWatch logs is that for the CloudWatch log, you can actually stream all of those log entries to either Amazon Elasticsearch, or you can actually stream that to AWS Lambda. So what we had is, you have a Lambda, they're going to be subscribing to the CloudWatch logs and going to stream all of them to elk stack. And you don't want to have a manual process, because you can do that by logging in and clicking, or you hitting against the API, AWS APIs, but it's going to be painful. What you can do instead is enable CloudTrail. And CloudTrail, what it gives you is any event that happens on the system in AWS, for example, creating a new resource, updating, deleting, somebody logs in and so on, is going to be published as an event. So now you can subscribe to it as any CloudWatch event, and you can have another Lambda that's responsible for doing subscribing for you automatically. So whenever a new log group is created, it will subscribe that log group with a Lambda that will ship all your logs to LStack. So now you just have implemented once, small Lambda, and it just works. You can also filter it so it only ships, for example, Lambda log groups. You can have a filter about what should be shipped. But the thing keep in mind is that when you're creating a new log group, the expiration is actually set by default to never expire, so it could get costly in the long run. So as part of that, when the new log group is created, you can also update this. You can do many automation bits of those events. And if you want to have a bit more read and play with it yourself, there is a great blog post by Yan about the centralized logging, and if you just follow that link below. And now we're getting to distributed tracing.
Thank you. So it's all well and good having all the logs for all of your functions, but for many of your features, you have to rely on multiple functions all working in perfect tandem for it to work. From the moment someone creates a post, for example, you have to go through multiple functions and multiple different event sources before the data eventually gets to where it needs to be, and for someone to then build a core and API to fetch their timeline. So now what happens if somewhere along the way something went wrong, and one of your QA guys or one of your users raised a complaint that, hey, my wife created a post last night that I really wanted to see in my timeline, but it doesn't show up. Why is that? To try to debug it is quite difficult, even though you've got all the different logs for all your functions, but it's not easy for you to string together everything that happened for that particular post so that you can see a chronological view of everything that has happened across your entire architecture for that particular post. Again, this is a common problem people find in the microservices. And the solution there is to use correlation IDs, which can include any number of things. It could be a user ID, the person creating the post. It could be the ID for the post that have just been created, and so on. The interesting thing to remember here is that the data that has been created is moving around your system through HTTP calls, through Kinesis streams, through SNS messages. That means all the correlation IDs that have to go with that data flow have to flow through all of these different event sources as well. And for HTTP endpoints, we know how to do that. We just pass them along as HTTP headers. But what about some of these other event sources? That's where you don't have obvious way to tag all this context data around with the data itself. And the way we approached this was to create our own libraries for HTTP by wrapping around our favorite HTTP client, as well as wrapping around the AWS SDK client for Kinesis, for SNS, and so on, so that on the publishing side, we can shove, for example, for SNS, we can shove those context correlation IDs into message attributes when we publish a message into SNS. For Kinesis, there's no obvious places to put them, so we include them as part of the message payload with a specially convention underscore context or something like that. And for HTTP endpoints, pass them along as HTTP headers. And on the receiving side, we also have a middleware tier in our code base where we will extract those, and then we set them as a global context so that every time from our code, from our function, we write a log message, those will be included as part of that log message, which in this case would be JSON string, so that when the log shipping function picks it up, you can actually add a lot of context to the log messages that you're sending to Elasticsearch. So that way, someone comes along with a question, hey, so-and-so's user ID created a post yesterday, didn't go to where her husband's feed, what's going on? Then you can start looking for that user. You can search for that user's user ID and maybe in the post ID as well to see everything that happened in your system for that particular post. Again, I've been writing a lot of stuff on Lambda, so there's a blog post that shows you how you can actually do that, including the demo code for both the client libraries as well as the middleware that you can use. Another aspect of distributed tracing is understand where the execution time happens across your function invocations. And for that, again, is a common problem people have in the microservices, whereas in the sort of serverful microservices world, tools like Zipkin is kind of the standard there. With Amazon, they also introduced the X-Ray, I think 2 years ago. With X-Ray, you can see for one function invocation, with instrumentation on your code, you can see all the different segments of how much time it took to, say, talk to SNS, to talk to DynamoDB, to talk to some internal API, and so on. And from that data, you can also see a service map so that you can see all the different services that your Lambda function is talking to, as well as the average and max execution time for those services. The X-Ray is all right. It works quite well for a certain set of things that it does. But one of the big problems I find right now is that API Gateway doesn't natively support it. So I'm going to step out of the microphone range, have a shot a little bit. So for this example, where I'm talking to another Lambda function by calling the Lambda API directly, and I can see everything that happens inside that second function. But when I call another function via HTTP API Gateway, then I lose the insight into what happens inside that second function. That said, API Gateway support is coming, I've been told. I don't know when, as Amazon typically do, so just wait for it. Another thing X-Ray doesn't support is it doesn't work with event sources that causes asynchronous event invocations. So if you're sending something to SNS, that gets picked up by another Lambda function, you don't see that second invocation that happens as part of your trace. There's a number of tools that are being worked on by people that are trying to bridge the gap that we have in the tools that we have in this serverless observability space. I'll talk more about that some other time. And for now, if you want to read a bit more about API, X-Ray, what's good about it, what it doesn't work, I wrote a blog post recently as well. How are we doing on time? I think we're okay. So moving on to monitoring, one of the things that we used to doing, on the serverful space, is to install monitoring agents and daemons to collect logs and to collect the metrics. Unfortunately, with Lambda, you can't do that anymore. You can't access the underlying host operating system. Instead, you are more reliant on the information that you get from CloudWatch, which gives you the basic set of metrics that you probably want anyway. And then other providers also started to support Lambda, but most of them just use the same set of data you get from CloudWatch, but give you a better looking dashboard in front of it. And in this space, the guys at IOPipe, they do something slightly different. It's quite interesting in that they give you SDK where you can have a factory function essentially to wrap your function code around so that they can intercept your function invocations and then send metrics to their own backend systems when your function finishes, either successfully or with some exception. And you can also get additional data points around the memory usage as well as CPU usage, which may or may not be of interest to you. But the problem I found with this approach is that because with Lambda, everything has to happen inside your function's invocation. There's no background processing anymore. So where IOPipe is sending metrics to their own backend system, you are paying for that invocation time. In fact, not only you are paying for it, because API Gateway doesn't respond to the caller until your function's invocation finishes. And whilst that's happening, some poor guy is using your app is actually waiting for you to finish sending metrics to IOPipe. So that's my main concern with the approach that guys like IOPipe has gone with. Because again, we don't have background processing anymore. We can't do all these shipping logs and sending metrics in the background. There is, however, a workaround which I find quite interesting. One of the things you do get the background processing for is the other things that the platform gives you, including collecting logs from standard out and shipping them to CloudWatch logs. So what you could do, and this is what Datadog does for custom metrics, is record your metrics as specially formatted log messages so that you can then process them asynchronously in the background outside of your function's invocation, so that the same function that is shipping logs to Elasticsearch or wherever can also then send those metrics to your metrics monitoring system instead. It's not the right approach for every scenario, but for user-facing APIs, I think this is something that is worth considering, because ultimately you don't want your users to be waiting for you to do this background processing. But for things that are invoked asynchronously, things like Kinesis events or SNS messages, you probably don't care about actual 10 milliseconds of execution time. Just fire all the metrics as you want. Again, you can try yourself. We have got some demo code and so as a blog post that explains how this might work, so you can try it out yourself. And once you've got all your metrics, you do the same things that you've probably known to do already, setting up dashboards, setting up alarms, and also any sort of application level metrics like the number of posts people have downloaded, have viewed, has created, also track those as well. However, as much as CloudWatch being a decent, fairly cheap service to use to monitor all of your Lambda functions, and also in most cases it's the only way for you to get metrics about Amazon's web services. So your DynamoDB metrics, your S3 and so on, they're only available through CloudWatch. However, CloudWatch is lacking on a number of different fronts. The UI is not great for anyone who's ever used it, and there's not as much customization options as you find in other services. And it also doesn't have some of the more advanced features like predictions that you find with Wavefront and Stackdriver. But a big reason for not using CloudWatch for me is that it's got a tendency to go down at the same time as the thing that you're using it to monitor. This happened to me a few times where, okay, Amazon's having some networking hiccup, but EC2 is down, or not working 100%, so I know my services are being interrupted, but I have no idea how bad it was, because also CloudWatch was also down. And sometimes when your service comes back up and CloudWatch is not, you have no idea, okay, is it working, is it not, what do we do? So that's not a great place to be. And with that, I'm going to pass you back to Domas.
So now we're coming back to the mentioned configuration management, because now you have many Lambdas running in production and so on, so it's all good and fine. But how do you easily and quickly propagate configuration changes to all of them? So initially, you can just, when you're playing around, you can just use AWS console to, for example, deploying Lambda, you can set environment variables. We chose this approach because Serverless does allow you to set environment variables in your Serverless configuration for your project when you're deploying it. But it makes it difficult to share across all the Lambdas, because if you have 50 Lambdas using some config and you want to change it, now you have to go in and update all of them. And because they are specified during deployment time and per function. Also, it gives you no way to have, like, what's the fine-grained access. So not everybody should have access to it. But if you're using environment variables that are required during deployment time, now all of your developers need to have access to that. Or else they have no ability to deploy. But you don't want to have somebody leaving the company, taking their codes with them on their laptop, and then having all the secrets there. So you want to have some kind of a centralized configuration service. It could be as simple as some key value store. So we had a look at what's available out there. We had a look at console. We had a look at etcd. But the thing is, you still need to run instances for these. It's going to cost you, even though if you're not using it, and to learn how to use, to configure, and how to maintain is quite steep. So in our case, because we already knew how to build Lambdas and APIs, so we just did our own small, so there was no infrastructure to run. It was really quick and small, but this was before AWS announced that they have parameter store. Now, this is a great thing, and you should be using it. It gives you a way to encrypt the sensitive data in flight and at rest, and it also is role-based access by IAM roles. So this is achieved by, so you have your admin, who is the only one, for example, in an organization who can update your secrets. So he can get access because of his IAM roles, and then developers don't need to access to change them at all, because all your secrets are being stored in parameter store, and then they are encrypted at rest using KMS. And when you are deployed your Lambda, when it starts up, now Lambda now has read access, and you can specify that specific Lambda has only for the secrets that it needs to access and not for everything in this case. So it's all good and fine, but it's quite, you still need, for example, how do you cache, how do you poll, and so on, because you don't want to be hitting on every request, you don't want to be hitting your configuration service. So in this case, we built our own small library for that would be responsible for fetching the information, caching it, so it only being initialized during the cold start of your Lambda. So the next time it's being called, it already looks up, it has in its memory, it can use it. And then it was also responsible for invalidating and refreshing them at some period. It could be like a couple minutes or so. And another thing, listening to signals. What I mean by that is that, for example, your Lambda is hitting some HTTP API. So it has the URL for it. It has some secrets for it. And then if suddenly you start getting back 404, you could raise a signal, and then your client, for configuration client, will invalidate that URL. So the next time it's being called, it will try and get the new value, because if you got 404, probably it moved somewhere. Also, if you want to see how it could be easily implemented, there are code examples and everything, how to use it on Yan's blog. I think we still have 10 minutes.
Okay. As you can see, I've been writing a lot. So I guess we've got 10 minutes, but I'm conscious of time. I want to give you guys some time to ask questions as well. So I'm going to skip a few of these, but one of them it is worth remembering and mentioning is that Amazon Lambda has got a 75 gig regional limit on all of your packages for your AWS Lambda that you upload. And and you may think 75 gig is quite a lot, but we found that because with Lambda and serverless, its deployment is so easy, and we were easily deploying functions hundreds of times a day each. So even with 2 meg package sizes, very quickly we will run into, I think at one point after about 3 months, 6 people, we had about 20 gig of deployment packages on the Lambda. So pretty soon we're going to hit that 75 gig limit. And so at that point, I took a leaf out of Netflix's playbook. They got the janitor monkey that goes around and kills resources that you don't use. So I wrote a janitor Lambda function that would run on a schedule and then clean up all versions of your of the deployment package for your functions that are no longer referenced. And one of the things you can do nowadays with version 1 of the serverless framework is also to say that when you do a deployment, don't always create new versions. Therefore, you don't create redundant packages for every single version, which in deployment or in development environments are just not useful at all. You want to turn it on for production, sure, so that you got a version that you can quickly roll back to, but not for not during development. Another thing that you can do nowadays, since 1.16.0 version of the serverless framework, is if you install your serverless framework as a dev dependency or anything as a dev dependency, they get excluded as part of the package step. Where if you're using the AWS SDK and you don't want to use your own you don't want to package your own version, you can install as a dev dependency, and that will be excluded. So your package size becomes smaller. And with the serverless framework, you can also invoke functions locally using the invoke command. And that means you can also, if you're using Python or Node.js, it also means that you can hook it up with your Visual Studio Code so they can actually debug your code locally. You can do the same thing with the SAM framework as well. With SAM invoke, there's also a way for you to just hook up your Visual Studio Code so that you can debug your functions locally, which is that. Okay, and with CoStar, this is probably the pain for everyone who's using any form of serverless technology today. And so CoStar is basically what happens when you runs for the first time. Amazon's going to have to load your code, have to start a container under the hood. Yep, we saw containers under the hood. And so that time is what we normally call a cold start. Amazon doesn't talk specifically about what happens in that cold start, But the OpenWhisk guys have talked quite openly about the different stages of ColdStart, where it's going to have to load up a container to run your code, and then it's going to download your code, and then it's going to initialize the runtime. So when you're using different languages, there's a massive impact on how much ColdStart you experience. I did a bunch of experiments earlier to find out how the language that you use, as well as the memory setting you use, affects your ColdStart time. And that one is C#. We're running .NET Core 1.0 at a point, and this is Java. By comparison, look how small Node.js and Python is. And that's one of the things that really maybe me being a .NET developer by trade, and you probably heard me going on here blabbing about F#, how great it is. I still think F# is my favorite language, but when you're working with Lambda, there's a massive penalty you have to pay. Well, not you, but your customer have to pay in terms of the experience you get from your application, which is why when it comes to Lambda, I have really embraced the use of dynamic languages like Node.js and Python. And again, what about type safety? Well, nowadays you can use Go, so they give you some type safety, not the same ones you get with C# and F#. And you probably heard me go around the NDC conferences telling people you should use F# type system to make invalid states unrepresentable in your domain. What happened to you? Well, I think the thing I found is that with a traditional Node.js application, you can make things really, really complex really easily. The complexity ceiling is enormous. But when you have a really constrained execution environment and you have to write your Lambda functions and deploy them in very small units, the tools that I really enjoy from F#, the sort of type transfer influence, the different types I get, they are there for me to help me manage complexity. But when you can really constrain the complexity of the things that your developers can develop, well, can build, I find that I actually didn't miss all the things I love about F#, which for me is kind of painful to admit at the same time. And with that, I think we don't have about 5 minutes, so I'm going to skip to the end where I thank you for your time and also give you a shameless plug about a course that I've been working on with Manning, where I talk about basically all the things I've mentioned so far, including a bunch of other things around canary deployment and other things that you need to know to be production ready, running AWS Lambda in production. And whilst in the early access with Manning, you can also get 40% off as well. So shameless plug over. Now is your time to ask questions. I think that's the mic going live. If anyone got a question, just raise your hand. Or is it too late, 5 o'clock, it's time to go home?
So do you do any warm-up?
Okay, that's it. One question.
Just a quick question.
That's fine.
So are you doing any warm-up yourself to get around the cold start issue, or are you just accepting the hit on the first invocation?
Sure. Good question. So the question is, do we do any warm-up for our functions to get around the cold start issue? The answer is sometimes. So for functions that are seldom, API endpoints that are seldomly exercised, that means chances are every time someone hits the endpoint, they're going to hit a cold start. For those, we do have like a ping function that pings them with a special message so that the function itself knows, the middle tier for the function knows that, okay, this is a ping. I shouldn't try to execute the normal user flow, which most likely going to fail. But for most other functions, even though we still do that for all the API functions, not for Kinesis or SNS and whatnot, for those other ones, we find is less effective because when you have concurrent execution for the same function, you have no easy way to find out how many concurrent executions are happening. So when you're trying to ping them, you only get one of them at one time. So the other 4 can still gradually be going to cold start. And Amazon Lambda also got this thing where it garbage collects the functions that have been idle for a while. And that tends to be every 5 minutes or whatever. So for busy functions that are constantly spawning new concurrent executions, you have very little chance of actually hitting the right one to keep them warm, or to maybe don't need it. The few cases where I think it is useful is, for example, if you are doing a food ordering service like Just Eat, where you know the peaks of the traffic where that happens, lunchtime, dinner, massive peaks. So if you let them happen as it normally would, that means all the concurrent execution that gets spawned during those peaks, everyone that hits those your API is going to hit a cold start. But if you know when that's going to happen, you can easily schedule a cron job that happens, like, say, 5 minutes or 2 minutes before those peaks and just spam your API so that you cause the Lambda to API gateway to create all this concurrent executions, so that by the time the actual user request load comes in, those concurrent executions are there, so that's how you can mitigate cold start for those specific cases. But if your spike in traffic are not predictable, then there's very little you can actually do besides using Node.js or Python or Go, where the code size itself is actually very small, and really just optimize your functions so that they don't they do very little outside of the actually have to handle the function code, like shipping logs and whatnot, all of that, metrics, and also just optimizing the dependencies so that you don't have so much dependencies, especially for JVM and C# projects where the more dependencies you have, even if you're not using on every single execution path, they still takes up the time to warm up your application with the virtual machine. Very long answer to a simple question, but it's not a simple question, to be fair. Any more questions? Okay, follow up.
The correlation ID problem you described, that sounded like a very tricky problem to solve. How long did it take you to actually figure all that stuff out, and are Amazon doing anything to make that easier?
Okay, so the question is, correlation ID seems like a tricky problem to solve, and how long did it take you guys to fix it, and is Amazon going to do it for you? As far as I know, Amazon is not going to do anything for you to fix that particular problem, because a lot of it is to do with how do you collect those correlation IDs. Like moving them around is one problem, but also capturing them and making sure that they go into all the logs is something that you have to do. As for the shipping them around, Amazon, as far as I know, is not going to do anything there for you, but it actually didn't take us very long to implement the system that we had in place. For starters, I actually implemented a similar system at the previous companies, so I kind of know what to expect, because this is something that even if you're not using Lambda and you're using services, you're running your thing in EC2, but you're consuming SNS or consuming Kinesis events, you've got the same problem. With Lambda, you just have to work out. Actually, with Lambda, it was easier in the sense because you don't have to worry about concurrency. One thing comes into your function, one invocation, there's no concurrency happening, so you don't get multiple contexts coming in, apart from Kinesis when you got batching, but that's something that you have to figure out how to do yourself. We did it in a certain way with some trade-offs, but I can talk to you about that afterwards. But for everything else, it means for Node.js, I can capture the incoming context objects, context IDs, correlation IDs, and shove them into a global variable. Since I know there's only going to be one execution, I can just put stuff into that global variable to my host container without having to worry about concurrency, getting wrong correlation ID between different executions. But yeah, it didn't take us very long. I think it was like a week, less than a week for me to put something in place. If there's no more questions, then I guess thank you very much again for coming to this talk.